It's a pleasure to be back in Bologna. And today, actually, I will show you some of the results of my last project that I developed together with Sarah Ellison and many others at the University of Victoria in Canada. And I will talk about the interconnection between galaxy mergers and quenching of star formation. Why we think that there should be a causal connection between mergers and quenching. So theory has long been predicted that there should be this link. And in this slide from Hopkins et al. 2008, it explains why, from the theoretical point of view, we believe that there is this link. In the central panels, there is the star formation rate and the luminosity evolution as a function of the time. For negative time is the pair phase before the coalescence phase, and after zero is the post-merger phase, after the two galaxies are combined together to form a single galaxy. And you can see the evolution of the two parameters as a function of the different stages of the mergers. When the galaxies start interacting gravitationally, the gravitational instabilities consume angular momentum from the gas, and the gas starts flowing towards the center of the galaxies. And this incredible amount of gas in the center of the galaxies trigger powerful episode of star formation that we call starburst. But at the same time, part of this gas, if the gas lose enough angular momentum, part of this gas feeds the central black hole, triggering powerful AGN feedbacks. And this former generation of models implemented AGN feedback that were so powerful that basically were able to get rid of all the gas in the galaxy, leaving a dead galaxy, and with the morphological transformation, a dead elliptical galaxy. So the point is, what of this picture of mergers can be observationally confirmed and what instead is still blurry? And I can tell you, and I will show you shortly, that up to this moment, theory and observations get along very well. But the point of casually connecting the mergers to the quenching phase is still very unconstrained. So let's see these. So first of all, asymmetry enhancement. During the interaction, as soon as the galaxies start interacting closely in the pair phase, and after some pericentric passages, the systems starts developing shells, tidal features, and so on. But even in the galaxies that do not show these powerful and strong features, there can be some asymmetry in the post-merger, in the mergers and in the phase. Here, for example, one of the studies in which you have the asymmetry as a function of the separation, the projected separation of the two galaxies, and in red for the merger population, interacting galaxies, and in gray for a controlled population of not interacting galaxies. And in the bottom, the ratio between the two, showing that the post-merger and the paired galaxies show enhanced asymmetry, and the asymmetry increases as you approach coalescence. So asymmetry is well confirmed. So not only in these very beautiful pictures, but for all the mergers. Another interesting thing that is strongly confirmed by observations is that mergers trigger AGN star formation rates. So after the first pericentric passage, you have that this gas is really flowing toward the center. How we know that this star formation rate is triggered by drifting gas? Because together with the enhancement of the star formation, this is again as a function of the projected radius, there is also a dilution of metallicity. And this is as well a feature, an imprint of mergers, all the mergers. So you have enhanced the star formation rate and metallicity dilution. The metallicity dilution is due because you are breaking in the center of the galaxies, pristine gas from the outskirts. So this is another, and there are plenty of works finding results like this one. Then mergers as a triggering AGN processes. So here the things get a bit less robust, in the sense that it is a pretty well known nowadays that depending on the selection, for example, here in this work of Ellison, we have that 60% of mid-infrared AGN selected host mergers, or at least we think that they are mergers. And the AGN fraction increases as a function of the merger mass ratio. So it is for sure, we know now that mergers can trigger powerful AGNs. The point is that it is still debated whether mergers are the dominant AGN process for triggering AGN. And here there is a strong and interesting and sparkling debate on this subject. Just one thing, that we are now able to predict the behavior of the new modern theoretical cosmological simulations, and we find as well in new modern cosmological simulation that there is an enhancement in the AGN luminosity in the post-mergers. However, is not as powerful as this in the previous generation of models, and we find that more or less around 10% of the powerful quasars are actually mergers or post-mergers. So yes, mergers can trigger AGNs, but they are not the major triggering process of AGN. And now we arrive to the point of this topic, that is, do mergers lead to quenching star formation? And I remind you just briefly that this generation of models more or less implemented a very similar AGN feedback. But on the other hand, in these models, the universe created by these models weren't very similar to what we actually can see in the real universe. For example, they are not able to reproduce most of the scaling relations at redshift 0 discovered with the Sloan and other surveys. And proving a causal connection between mergers and quenching is super challenging. And here I'm trying to convince you that this is the case. So this is again the sequence, and here I'm highlighting in blue the part where is it possible to observationally find and measure some kind of disturbance in the morphology of the galaxies. While in red, I'm showing what is the time scale where we can nowadays connect the galaxies to quenching. That is the post-Arpast phase. So the post-Arpast are the best population of galaxies that show powerful, stronger absorption in the Balmer lines, indicating that their spectra is dominated by A and F stars. So that means that there was a recent star formation that has stopped around 0.5 and 1 gigayear before, and no sign of star formation, and most of them are nowadays linked to some kind of disturbance. So it's possible that many of the post-Arpast could be post-merger galaxies. Anyway, here the point is that if you want to understand if the two populations are connected, if the merger leads to quenching, you have only very short overlapping between the time scales, and so this makes this task very challenging. And so far, most of the studies focus on understanding what's the fraction of mergers in the post-Arpast population, because it's much easier to, especially now that we have the Sloan and the other surveys, the spectroscopical surveys, it's much easier to study the post-Arpast population. And so the point is that when you look in the literature, you find very different results that goes from almost zero post-mergers in the post-Arpast population up to 60%. And actually, in this paper in Wilkinson et al. 2022, there is a very nice, let's say, overview. It's not a review, it's an overview of the methods that people use to do this kind of studies. Anyway, even if in the extreme case that 100% of the post-starbust are post-mergers, this doesn't tell us if all the mergers quench, because they are different populations. So we are interested in the complementary question. That is, what's the fraction of quenched galaxies in recent post-merger galaxies? Can we answer this? This is like, later on I will talk about very recent observational results that we got in UVic. But for now, let's pretend that no, it's until 1 year ago, the works trying to address this question were zero. So we approached this problem using prediction from cosmological simulations. So cosmological simulations, modern cosmological simulations, we analyze 3 different cosmological simulations that implement similar accretion onto the black hole. All of them use a simple model of Bondi accretion. So Bondi is sorry. Anyway, yeah. So these are 3. Because there was the Y on the whole. But anyway, this is a Bondi, not Bondi. Anyway, so all these 3 simulations use a very similar approach for the accretion onto the black hole, but they implement a very different and peculiar AGN feedback modes. And since this is like a drawback of cosmological simulations, but there is no way that you can quench simulated galaxies without invoking AGN, a sort of a form of AGN feedback. And I said drawback because we don't have any confirmation from observations, but it's, let's say that it's kind of obvious to think that you need like some sort of a powerful source to quench a galaxy, either by expelling the gas from the galaxy or eating the gas and the CGM in order to prevent the new gas to fall in the center and trigger star formation. So the point is analyzing 3 different outcomes where in none of them the mergers were implemented, were modeled, but the mergers are outcome and provisions of the simulations. We try to understand what's the impact of mergers on the quenching star formation. So we selected a complete sample of post-mergers in all the 3 simulations. Here are the main parameters. And we selected where only the star-forming post-mergers that were in the star-forming main sequence at coalescence, massive post-mergers, more massive than 10 to 10, so that they could have a control at most of 10 to 9 solar masses, mass ratio larger than 0.1 and redshift below 1, and with controls of non-interacting galaxies, very important to understand, to take control of what you're doing, with stellar mass and black hole mass within 0.1 dex. And N2 is a parameter that gives you like the number of galaxies within 2 mega years. It is basically a measurement of the environment, of the density of the environment. So with this, our approach is very straightforward. So in cosmological simulations, we can study the evolution of the parameters. So here there are 3 examples. In the first case is a galaxy that after coalescence keep forming stars all the time till the simulation ends. Here, another example where the star formation rate drops almost immediately after coalescence, and another case where you have an intermediate situation. So if we do this for all the post-mergers and for all the controls, at each time post-merger, we can count how many of them keep forming stars and how many of them are quenched, and then analyzing what is going on. So we did this, and this is the result. On the y-axis, we have the percentage of quenching galaxies as a function of time post-mergers for the 3 simulations: purple for EAGLE, Illustris in green, and yellow for TNG. So you have like that within 500 million years from the merger, you get that only TNG arrives to at most 10% of post-mergers that quench. And this, by the way, is the moment where the mergers affect the galaxies most. So after this, basically, you can consider the rest as a normal galaxy evolution. So the paradigm in the simulations changed a lot since the previous generation. While we had almost 100% of post-merger quenching, here we have at most 10%. But if you focus on Illustris show like that there is a deficit, because if you have if you look like here at the dotted line is the control. So you have that within 500 million years, you have that the controls quenches more often than the post-mergers. So it's pretty clear what is going on here. And if we do like calculate the ratio between the two, between the post-mergers and their direct control, we can understand what's the quenching excess of galaxies. And what we find is exactly that while IllustrisTNG and EAGLE show enhancement with respect to the control population, Illustris show a deficit of post-mergers. So it's true that mergers do not lead very often to quenching in these modern cosmological simulations, but yet there is like an enhancement with respect to the direct control population. So I told you like that it's very difficult doing this from the observational point of view. But actually recently there was this paper from Bickley et al. 2022, where using unions, that is a survey in the North America, I believe, and spectra from the Sloan, they visually confirm like a sample of robust post-merger galaxies, around 3,000 post-merger galaxies. And using this sample, Ellison et al., in this paper, we could be able to do like a very similar experiment in observations. And here I'm showing you like the excess of post-starburst in mergers, again, as a function of the projected separation. One thing, first of all, you see that in the pair phase, even when the two galaxies are still separated but very close, you don't have basically any excess of quenching. But when you end up in the coalescence phase, using two different selection approach, one that is E plus A, that is the standard approach for selecting post-star galaxies, and the principal component analysis, you find a very strong excess that is kind of in contrast with what we found in cosmological simulations. And we can do also a comparison. So here I'm comparing in the top panel the percentage of quenching post-mergers and the quenching excess in the two experiments. Here in orange and in blue, the results, the observational results are indicated as lower limits. They are lower limits exactly for the reason why the overlapping between the two time scales is very tiny. So the number of post-mergers that are also post-starburst is a lower limit by definition. And there are also some other reasons, but that's the most important one. So, and you see that even in the most conservative one, the E plus A selection, it is a pure sample of post-starburst, but is strongly incomplete because it gets rid of all the galaxies that have even a small amount of star formation or new star formation or lines that come from a nuclear ionization. And so even in this case, we can't reproduce the observational result with cosmological simulations. And the same also, the quenching excess, only EAGLE with huge error bars can get closer to the results from the observations. So this tells us that despite the simulations are able to reproduce even the quenching population, the overall quenching population, most of the scaling relation at redshift 0, they struggle to reproduce these little nuances that come from populations like the post-starburst or the post-merger galaxies. And but you can say, okay, but maybe like the experiment is not exactly the same, the matching scheme can change. So we did like this experiment. We tried a bunch of different approaches getting closer and closer to the observational approach, that is BM, that is matching only in stellar mass, redshift, and only major mergers. And you see that even in this case, we are closer, but never compatible with the selection here, and absolutely far to be compatible with that. And similar for the enhancement. So the point is, why we can't quench galaxies merger in the simulations? Here I'm showing you the result from EAGLE, and if there will be time also for the other two. But anyway, so these are 4 parameters, very important parameters for the mergers. There is like this, the halo mass, and the gas fraction, and the mass ratio, all of them as a function of the black hole mass. Because all the models, the AGN feedback models that I introduced earlier, they somehow, since the accretion rate onto the black hole, it depends on the black hole mass in the bond accretion, the black hole mass represents a sort of integrated history of AGN feedback. You can imagine this as a sort of the final result of many episodes of AGN feedback. If you look at this, so basically as the black hole mass grows, you expect more powerful AGN feedback. So you expect that with increasing black hole mass, you increase the frequency of quenching. But this in EAGLE is not happening. There is a window where the numbers are increasing, but most of the galaxies keep forming stars. And not only, another thing is that most of the post-mergers in EAGLE have low black hole mass. They have low massive black hole mass. So that means that they don't have enough energy in the feedback and the output for quenching the star formation. But there is also another interesting thing that we found. That is, as you go to very high black hole mass and very high halo mass, let's say groups or even clusters, the number of quenching post-mergers drop almost to 0. And this actually is something that we found happening in the EAGLE simulation. That basically the AGN feedback in EAGLE is only in thermal mode, and this gas hits the circumgalactic medium, but actually not enough to completely shut down so the cooling time in the CGM is so short that basically the AGN can't compete with the cooling down of the gas. So this is why in EAGLE we don't find many post-merger that quench. But if you look at the gas fraction, you see that below a threshold of 0.01, most of the galaxies actually are quenching. So you need like a sort of an AGN model that is able to be powerful enough to get rid of the gas. If you don't get rid of the gas, you keep forming stars. And this is true for all the simulations that we analyzed. I will come back to this later because I don't have much time, and it's not very interesting. But in TNG, we found the same. So the galaxies quench when they are they have a supermassive black holes, and they are below a threshold of gas fraction. So this can tell us something. And again, here the vast majority have one thing. In TNG, the AGN is in 2 modes. Below, let's say, below 10 to 8.2 by construction, the mode is only thermal. So they bump thermal energy into the ISM, and this energy is completely dispersed all over the galaxy, and it really poorly affects the gas. But as you get to lower accretion rates, and these lower accretion rates is regulated via a switch that contains as a parameter the black hole mass, and the switch happens around 10 to 8.2. Above this threshold, you have a switch in the mode of the feedback, and you start kicking the gas with injecting momentum in the gas. And so, and it is here that the model of TNG becomes effective in quenching the galaxies. And this is pretty much what we are seeing, that as as the AGN, the low accretion rate triggers the AGN feedback in low accretion rates, you see like a very effective quenching in the post-merger population. And they quench because they lose the gas, because this momentum blows out the gas from the galaxy. So we then analyzed that. This is my last slide. So why? So what's happening in the gas? So because so far we see why they do not quench, but the few that quench, why they quench? We see that they have like a very low gas. So what was the gas fraction at coalescence? So here in blue, green, and red is star forming, Green Valley and quench at the post-mergers. They were star forming at coalescence, and here there is the difference between the two. You see that there are two things that we found in both simulations. First of all, is that most of them already have a very low gas fraction, below 0.1. So you can say it's easier to quench a galaxy if there is a little gas to start with. And the second one is that the post-mergers that quench are the ones that lose much more gas than the others. If you look at the blue and the green, yeah, they lose a bit of gas, but not that much compared to what happens in the post-mergers. It's just that they are not that many as much as we want. So I skip that one and I leave you my conclusion. That is, in modern cosmological simulation, quenching is rare, very rare. And the few that quench because of the black hole feedback. And for quenching, the few that quench, they show a predisposition toward quenching because some of them have very little gas to start with, and they lose from a lot of gas promptly after coalescence, meaning that the mergers have the built-in mechanism of quenching of the simulations to quench the star formation. And these are the results where it's based. So I hope that this paper will be accepted in these days. I hope that it will also matter. Okay, anyway. Yeah, thanks.
Questions for the speaker?
You mentioned in the beginning the fact that you need to trigger the AGN feedback to quench the star formation. And so there is no other way to do it in simulations. But the simulations that you're using are cosmological, right?
Yeah.
Isn't it maybe a matter of you don't have enough resolution?
For sure, it's also a matter of resolution. Yeah.
If you do the same experiment with the galaxy scale simulations, is it possible to get rid of the gas with, I don't know, in the pre-merging phase, tidal stripping, or is it impossible? I don't know.
Without a gen, no, it's not possible. Even with the TNG 50 that has a very higher resolution compared to this, but also some other results that are zoom-in simulations, what you find is that if you don't implement an AGN feedback, you don't quench a massive galaxy. There is no way to quench simulated massive galaxies in hydro simulations to quench massive galaxies without invoking any kind of AGN. Yeah.
And are the trends you observe in Illustris consistent with, if I remember correctly, that with the fact that Illustris has a very excessive AGN feedback mode?
So IllustrisTNG
connected, not TNG, the first one.
Yeah. That's your guess is correct. So here I'm showing, for example, this is for Illustris. That is the one where there are no quenching in post-merger. Yeah, indeed. So basically, also Illustris implements a two-mode feedback, but the high accretion rate is again only dumping thermal energy that really poorly affected the ISM. And here you see that the post-mergers, that is the blue histogram, have high enhancement accretion rate onto the black holes. So basically, they are constantly on the high accretion rates, and so they do not quench because you are not affecting the ISM. So yes, that's very important.
Okay.
Maybe it's a curiosity. I'm very surprised why they implemented genetic in this way. It's like the opposite of what we observe in simulation. So when the gene is highly accreting, we have these hot bubbles that are strongly affecting the host and the gas content. And thermal is usually negligible.
Yeah. So this is true also for the TNG. So at low accretion rates, they have jets. They have these powerful jets. So TNG dropped like the idea of the bubbles of the elastics because that really there are many results that prove that elastics was dropped. But actually, the switching, the thermal energy is in TNG is basically the same as in elastics. So you have for 18-ton accretion larger than 0.05, you have there is a switch also there, depending on the black hole mass. But again, in high accretion rate, you have thermal energy.
But it's not surprising.
Yeah.
But I think the hot bubble in the low accretion rate is to mimic radio feedback in groups producing X-ray cavities.
Yeah, that's the point. So you have low accretion rates in that case, and you simulate these bubbles. The point of this bubble is that they only affect the CGM. So if you have something that is happening in the center, you find that out 3 gigayears after the fact. Yeah.
And you didn't mention anything about the recipes for star feedback because they are irrelevant to this.
For this kind of so that's what we think. My idea instead is that we are not so that's the idea because like star feedback is very important in small galaxies. But we are not talking about galaxies that are also in the opposite direction. So I just want to show you one picture, this one. So when you see these galaxies, they are far to be stabilized. They are not in equilibrium. So if you have like some sort of instabilities where you have like that the gravitational potential is not evenly distributed, I believe that something related to the stellar feedback could help, not only, but could help to quench part of the galaxy, but not totally. Yeah. So they are too massive for the stellar feedback in galaxies.
Is there any question from the remote audience or anyone else from the room?
Curiosity, the questioning the simulation, they all have the form selection. Yeah. But do you know if all terms are triggered as in EGN or quasar, or there's no accretion?
No, so in the post mergers we found the accretion basically in all of that. But I can show you like the result from the paper that I'm waiting from the accept. Is so that you see that most of them have high accretion and the volumetric luminosity about 10 to 4. And no, you can see my screen. I don't know. Okay. I can show you offline actually because if you have like okay, let's see. Okay, here. So this is like the fraction of the galaxies that at that luminosity have a luminosity above that situation. And basically you see that up to 10 to 44, to 43 and a half, most of the post mergers have accretion rates above that, feedback above that. And but so here, so there is an enhancement compared to the control population. But in another paper of our student, they study only the TNG simulation, and we found that there are only that up to 14% of the powerful phase are up mergers. So if on the one hand it's true that most of the mergers are powerful AGN, it's not true the opposite. That is the interesting question. If it is hard mergers that better trigger mechanism, and that's I believe that also in observation we are going in the same direction. Yeah.
Okay, then I think this is it. Thanks again. And I'm stopping.